So I'm going to talk about some concepts related to how scaling WebRTC applications involve load testing and what kind of takeaways we can take from that area. So as Lucan mentioned, I joined SignalWire in June. And I did a presentation actually some time ago in ClueCon in 2014, which was around Verto and using it with Camaillo. And it was one of the initial moments where Verto was available and one of my first experiments with WebRTC. And so I've been around this area for more than 20 years now. And there are two components that made me company through this journey, and it's mainly Camaillo and FreeSwitch. And by the way, in relation to FreeSwitch as MCU combined with an SFU, I did a presentation in 2019. I'll just mention it later. And my last presentation live and also my last live event was actually FOSDEM in 2020. So for obvious reasons, there was a little bit of a break, but now I'm very happy to be back. And also I'm happy that there were Ivan's and Luca's presentations today because they touched some very interesting points, also very well explained, and I can probably reuse some of this information. So WebRTC is an enabler of services. So we can talk a little bit about what kind of services this actually means, and some of the key performance elements depending on the service, as we saw also this morning. The type of optimizations that can be applied to when scaling the infrastructure. And the key elements related to the load testing and some practical examples of generating a large amount of calls, emulating either browsers or the activity that the browsers do at WebRTC level. And also, I'll show some demos. And as Stefan said, if it's going to fail, so I will apply automatically for dangerous demos and should, that's the plan B. So as you know, I mean, WebRTC is a group of protocols that can be used. Mainly, theoretically, you can use them as peer-to-peer. So if you have to a video call with WebRTC, you can actually just do it without any service in the middle. Actually, for example, Jitsi, when there are just which is an SFU, when there are just two participants, goes into peer-to-peer mode. So that's possible, but it's an exception. What typically happens is that there is a service in the middle, and only rarely it's one-to-one. But anyway, so small video calls, typical office collaboration scenario, or larger events like could be an all-hands in a company. It can be used for broadcasting and streaming with the differences that also Luca and Ivan mentioned when the focus is more on low latency. And other cases where, for example, there are only a few publishers of the streams and a large number of audience. And in case where you do want the users in the audience to be engaged and when latency is critical. Then something that, I mean, it's famous because of Stadia, but something that I stumbled upon and was a nice surprise was smaller companies providing online gaming through WebRTC. So basically streaming the video of the game through WebRTC and having the users interacting through data channels that I found very interesting. And of course, in this case, latency is paramount because of the interaction between the users and what actually it's a representation of the game through the video. And then also something more niche, like even services where people want to play an instrument together. And in that case, I saw that, of course, they have very stringent requirements, like they want to stay within 80 milliseconds, which, of course, it's possible depending on the geographical position of the users. But that was also good to see, and also medical in case of very low latency and reliability. So depending on the type of service, then there is an impact on specific characteristics of the system that you are building. So in terms of topology, of course, geographical distribution, and in particular, the latency that is allowed for to be experienced basically end-to-end. And of course, there is a difference if it's only audio or audio and video. That's a very big differentiator. And the level of interactivity that is required with the users. So just to give a very rough example in terms of latency requirements, you can see that for very interactive gaming or music, you want to stay within 100 milliseconds. For video calls and some types of surveillance where reacting is in real time is very important, then you can stay possibly 500 milliseconds is good, is still good, but a little bit more, surely below the 1 second. And then real-time streaming with some type of interactivity, as Luca was mentioning, like related to being able to reference to a specific slide, then you are going to stay possibly within the second a little bit more. And then the more traditional streaming where you can go above 5 seconds and it's almost negligible for the audience. But as we are talking a little bit about scaling, and then we know from the industry that one typical approach to scaling, in particular with SFUs, is to generate a sort of cascading of the servers where a few publishers, or anyway the streams that needs to be published, are basically multiplied by going through different levels of basically multiplexers that generate a copy of the stream for the subscribers of the stream. And of course it's trivial to see that each layer is going to multiply the streams, but it's also going to possibly add a bit of latency, which is going to accumulate for the end-to-end result. So apart from the obvious capacity that you want to measure when you're scaling the infrastructure, there's the cost element, so the cost minimization element, which typically boils down to the ability to be elastic. So to grow, not to have the largest possible infrastructure, but to be able to grow up and down depending on the load. And then it really depends on the requirement in terms of geo-distribution and how much traffic is going to go across continents or distant areas, and how traffic can be partitioned accordingly. Of course, you want to keep the traffic as local as possible, and there are, depending on the scenario, there are strategies to do that. The resilience of the system is important, but also for WebRTC in particular, there is typically 5 to 20% of users are going to need a turn service, and that's a part of the system that needs to be provided anyway and needs to be scaled, either if you build it or if you use it as a service as you pay. So even Luca mentioned SFU versus MCU very quickly. So SFU is a router of streams and MCU is a mixer of streams. So that's really depends on the type of application that you're building and whether you want to delegate the composition, for example, of the video to the final client, or there are reasons for doing the composition in the mixer. But as you may imagine, mixing is more CPU hungry than just routing. And so here you have another compromise. And this is why I mentioned that presentation in JanusCon, because that was an example of using Janus, which is an SFU, integrated with FreeSwitch as MCU through their APIs, so that there could be a hybrid system where, for example, the web browsers could connect. So web browser from laptop connects to Janus, and for example, mobile devices get only one stream from the MCU from FreeSwitch. And of course, there are ways to prevent the encoding operation when it's not needed, because that's going to be one of the most expensive activities, more expensive than routing. But even for routing, as that was a very interesting presentation from Richard this morning about RTP engine, the ability to avoid the packets to leave kernel space when doing routing, that's going to save CPU and also latency. So that's a possible strategy for optimization. Anycast also is being used now. For example, a typical example is Cloudflare, where basically you have IP addressing that is dynamic. So basically, depending on the region where you are, BGP is going to route you to the closest POP. And so with the idea that once the path to enter into your system is optimized, then you can also have a better routing of the packets inside your system rather than relying on open internet for end-to-end. And of course, depending on the system that you are using, you can do internal profiling and optimize at component level. So in general, this also to say and to highlight SignalWire and also what Tony was mentioning in terms of the call fabric. So these elements are an indication of the complexity of building, and maybe give the opportunity to service builders to use products like SignalWire, or even build solutions that tend to solve the same problem of avoiding to building again and again solving the same problems. So in terms of load testing, this is similar to what happens in the VoIP, more traditional VoIP world, with some slight changes. But in general, of course, you're interested in estimating the maximum number of concurrent sessions that you can have in your system, because that's going to tell you if you can handle all the traffic that is required. And one key element is also the amount of new sessions that can be established in the same amount of time, which is, in the traditional world, is call rate. In this case, is more related to session establishment. And of course, how much time does it take to connect? In WebRTC, there are a few phases in the negotiation of the stream that require time, and they can adapt from the time somebody clicks on call or connect to the final establishment. That can also be impacted by load, and that should be minimized. And the obvious overall resource consumption in terms of CPU, memory, and bandwidth. And video, of course, is a big component, is a big consumer of all these resources. Together with that, when we're doing load testing, we need to be able to have results that are reproducible as much as possible, while there are some saturation mechanisms that can basically invalidate some tests. And then when you are automating the tests, you also need to automate everything that comes together. For example, for the SignalWire video SDK, you need to retrieve a valid token, which adds some time. And if you want to automate the test, you need to emulate the interactivity of the user on the browser, and automate the connection and joining of conference room, for example. But also understanding the quality degradation that happens, because that's going to happen before the system is not able to process calls anymore. In all this, also generating traffic is expensive because browsers are expensive to run. In addition to this, there are then special conditions that you may or may not have, like the need for transcoding, which is going to require more resources, and the ability to simulate degraded network conditions to see how your application reacts to that. And also, in particular for services that may have surges of connections in the same small time frame, like events or sports events, when people tend to connect all at the same time in a small amount of time, the ability of your system to cope with that is important. So in general, one first step is trying to understand what's the smallest unit that you can load test. Try to understand what it is, testing it, and then infer, given the scalability may be or not linear, but infer how can you then estimate the overall capacity. In general, though, of course, to making sense of the test results, you need to collect statistics and being able to visualize them. In particular, in WebRTC, luckily there is a plethora of extensions of RTP and RTCP that allows to get an understanding of how the client, which is in this case is the browser, is what it's experiencing, so what it's called the quality of service. And key elements may be related to how many times the browser asks for a packet to be retransmitted, or if there is, for example, a packet, a frame that was dropped, or a packet loss indication, because these are all elements that indicate possible networking issues. But in general, what you can also do is you can probably rely on the bandwidth estimator that is included in the implementation of WebRTC, because that's going to react to a bad metric related to, for example, a large number of NACs or frames dropped, by automatically reducing the bandwidth, at least momentarily, and then trying to re-increase it afterwards. So that's an indirect way of understanding how the browser is, what type of quality of service the browser is experiencing. But if you want to do something more sophisticated, then you really need to understand how the video is impacted. And then there are some techniques for that. Some rely, like this structural similarity, on comparing a reference image or video to what you are getting, but that's also difficult to reproduce because you need the reference image, and maybe not the best case to be used. And I saw also Dr. Alex time ago published a paper when they had a machine learning based system for estimating the variation of the video quality automatically by looking at the video without the need for a pre-known reference image or reference video. And so one important element is understanding what's the threshold by which you decide that the quality is not good anymore. Put it in relation to the load that the system is experiencing, and then draw your conclusion from there, and vary your requirements in terms of capacity from this information. So in terms of something a little bit more practical, so emulating WebRTC activity. So of course you can just use a browser, and we will see very quickly one demo. You can just use a browser and use your system. Of course, when you want to automate, you want to be able to automate all of that and have the system, have your system tested by something that behaves like a browser. Now, you can either really use browsers that are just the browsers without the GUI, basically the headless browsers with tools like Puppeteer or Selenium or Playwright. And the advantage of this is that you get for free the entire core of the browser. And so you can also stay up to date with the various versions. And you get for free also compatibility information. But of course, the browsers now are very resource demanding, so that's expensive to do. Or you can focus more on emulating the WebRTC client. So the part that basically establishes the ICE negotiation, the DTLS connection, and exchanges the media, which may be sufficient for the system that you are testing for having exactly the same load that you could have with a browser, but with less resources used on the testing side. And of course, the compromise is that you're not using a browser, and so you may miss something that is browser specific. So maybe you can imagine a combination of the two. This could be a good compromise where you have the real browsers always available for testing. Then you have the browser emulator for generating a smaller number of calls, and then the WebRTC client's emulator for a larger number of sessions. And then for the data collection, the usual thing or the reasonable things are available. So the logs that can be produced by the clients themselves, and a very important resource is the WebRTC RTC stats that are available from the WebRTC client itself. Of course, you can then map it to what you see on the hosts that you are using in your custom server-side reports. So this is, for example, this is how WebRTC internals in Chrome graphs what's provided by RTC stats from the client. And so all this information is actually available from the client API, and you can collect it and send it, and make the client send it to, for example, a collector of this information, so that then you can have basically correlate the data that you are collecting with the resources in use at that moment from the system. And you can see, for example, there's the frames dropped. So in this case, it's 0, and it could be a good indication that something went wrong if there were frames dropped, or if the jitter buffer increased, because that's the other thing. So even if you don't have a big packet, even if you don't have a high packet loss, but the jitter is very high, then the jitter buffer is going to increase, and then automatically is going to increase not the network delay, of course, but the end-to-end network. And so something that is not really related to the latency on the network is going to impact the end-to-end latency on the final application. And this was something that has been causing trouble in many scenarios. So one practical example, this is something Luca used time ago, and I'm reusing it. So it's Puppeteer, which is basically a Node.js application that can simulate Chrome, and recently also Firefox nightly. It's super easy to use. You just basically you install it in your Node.js application. You go to a page just providing a URL, and then you can interact with the page itself, and will bring up a headless Chrome for you, or headless Firefox. Or in this case, without a headless browser, with node-webrtc, another Node.js based. In this case, it's just using libWebRTC to behave like a WebRTC client. And if you want to do something more sophisticated with the media. You can interact with FFmpeg, so you can receive WebRTC media, WebRTC streams, and send it to FFmpeg for recording, or the other way around. You can have FFmpeg reading from a file and having node-webrtc encoding it and pushing it into the system. And then, so Google Cloud Functions is an example of something that, a serverless example that has been useful in the last months for the tests. And of course, it's not the solution, it's one possible solution. And the nice thing is that it scales very well, so you cannot worry that much about the amount of calls that you do to your functions. There are some limitations. So there is first generation and second generation functions. There are some differences in terms of timing, that the maximum amount of minutes that you can run the application, and other small things. I see I'm out of time, so I'm going to go to the demo. The main structure is this. So you have an application that runs the requests, which are simply HTTP requests. The Google Cloud Function that is triggered by the request connects to a web server to retrieve the tokens and to retrieve the page to simulate the user, and then interacts with the SignalWire API, gets the token, connects to the WebSockets system, and then interacts with FreeSwitch for the exchange of the media stream. And this is, I'll leave it in the slides, it's not really for now. This is an example of the dashboard from Google Cloud Functions with 100 node-webrtc clients having run for a few minutes. It's not particularly clear also because the dashboard has a little bit of a delay, but more or less the 99% of the clients used about 100 megabytes of memory, which is about 1/6 or even less than that compared with using headless Chrome. Yes, and this has mentioned that already. So in terms of demos, I'm going to show you very quickly. So this is just a reminder for me to show you the stats. So this is a modified version of the simple video API demo that you can find in the guides, and I put the link in the slides. So this is me connected, and then I'm going to launch three headless browsers from Google Function that are going to publish a artificial video into the room. Yes. So these are three publishing video into the room, and meanwhile they are also collecting the RTC stats that will be available at the end of the call. And then here I'm going to launch let's say 50 WebRTC clients from node-webrtc from another Google Cloud Function. This is not going to be visible because they are behaving as invisible watchers, but we can get an idea from FreeSwitch itself, like this. So you can see there are 16, 18, 20. So the members are, I'm producing about one new session per second. The session creation is not particularly precise. So you cannot have, in this way, very precise call rates. But nevertheless, if you are focused in particular on concurrent sessions, then you're going to be fine with something like 200 milliseconds or half a second or 1 second. So we got 49 members. So maybe one had an issue. But this is the case. So we have 4 publishers, 1 real browser, 3 headless browsers from Puppeteer, and 49 from node-webrtc. And so this is going to be produced at the end of the call. This is an example of the stats available. At the end of the call, you can get an idea of the RTT, 42 milliseconds, for that call that I had something like 30 minutes ago. 1 PLI request, so there was a packet loss indication that indicates a possible problem, and then statistics on the amount of bytes exchanged. And of course, these can be more complex depending on the needs. And so the takeaway points. So I think these are the 3 main elements. You may expect the WebRTC service to scale easily and just be used as you now use cloud infrastructures like AWS and Google Cloud and the others. I think we're not there yet, even though services like SignalWire with the platform and the SDK go in that direction of decoupling what you want to build with the actual building of the infrastructure. Testing WebRTC applications is more complex than just testing web applications because of the RTC part of it. And then even though there is some work to be done, there are relatively cheap ways of generating traffic and generating load testing for what you need to do in terms of scaling and estimating capability. And that's all I have. Oh, some reference, but it will be in the slides for who downloads them. That's all. Thanks. Questions?
All good?
No questions?
There's one over there. Daniel.
I knew it.
Oh, I'll use mine.
Actually, like 2 questions. One would be about the costs of those using like Google function services and so on. What we should expect from testing it, especially on the open source.
Mm-hmm. So first of all, they are designed for a very large number of calls. Like, for example, the first 2 million of calls of a Google Cloud Functions are included. So you got some billing from 2 millions. And then you pay for the amount of CPU resources and for the amount of memory with an initial allowance. So for example, I think I made an estimation, something like if you do 300,000 calls per month with about 75 megabytes per call, only the egress bandwidth is computed, but that came about 5,600 euros for the month. So it's cheap, and in particular, if you, it depends. If you are running the load test, I don't know, every time there is a new commit in a branch, that's going to become expensive. But if you do something like you prepare the release and you have a pre-production system and you go through the load testing, maybe you're not going to even need 300,000 sessions per month.
But that's a few thousand euro there, right?
Yeah.
Dollar is better now. It's strong. Okay, and the second one, hopefully, time. Can you actually do it like just between two endpoints and not going like through a media server like or SFU MCU, and you still get like reports? So just I want to run it from here, and I have also the endpoints maybe in the same Google Cloud function, and just to get the reports. Okay, I launch it, 12 calls, and I got connected 12 calls through the WebRTC, and get the statistics in terms of.
Yeah, I mean, you're simulating a web page in a browser, so you can program it to extract the statistics and send it wherever you want. So you can either have a callback URL where you send your information, and it will be part of the function itself.
Okay,
That's
thanks.
possible.
It will be more complicated, but you can, I assume. Thank you, Giacomo.
No problem.
Great speech. Big round of applause for our last speaker for today.